Welcome to APL 360. My name is Jamie. This video is part of my series on the APL 360 programming language. This episode is Basics for Rectangular Arrays. This episode will be looking at different arrays. Some of them will be just simple one-dimensional, but then we'll look at mostly two-dimensional arrays. This first array, P, will contain some prime numbers, 2, 3, 5, 7. We'll look at the shape of P. In this case, the shape is only one number, showing us that it is one-dimensional and it is of length 4. I'll set T to be a character vector, and we'll look at the shape of T. It's of length 5. We can concatenate P with itself using the comma. In the dyadic form is concatenation. We can concatenate T with itself. We'll try to concatenate T with P, but we'll get a domain error. We cannot concatenate characters with numbers. We'll create a two-dimensional array M. The way that we specify the shape that we want is by putting in the dimensions 2, 3 before the reshape or the row operation. And then we'll use more numbers here, 2, 3, 5, 7, 11, and 13. We'll display M. We'll see it's a 2 by 3 matrix. We can get a 2 by 4 matrix of characters by specifying the previous array T on the right-hand side. Remember, T was only of length 5, and so what APL does is it just keeps using the characters of T from the beginning to finish filling out the shape that we've specified. We can reshape our two-dimensional vector M into being one-dimensional a couple different ways. We can do 6 reshape M, and that will give us all 6 elements of M in a single vector. We can also use the comma operator in the monadic form. It's called ravel. We'll say ravel of M is also this 6-element vector. We'll set P gets ravel M. We can index into our vectors this way. We'll say P index 3, and we'll put left and right square brackets to specify the indices, specify that we are going to be putting in indices. And so the third element, and at this point, the initial index origin setting for APL is 1, unless you specify something different, and we'll see that later. We can put multiple indices inside the square brackets. So we can do one element 1, 3, and 5, and we'll get 3 elements as the result. The numbers 2, 5, and 11. We can use the index generator, iota, to generate indices here. And we see why that name has been given to iota used this way. So this will be elements 1, 2, and 3 of P. We see 2, 3, and 5 as the result there. If we want the last element of P, we can do P with an index of the shape of P. So remember above, that gave us the number of elements or the length of P. And so by specifying that here inside the square brackets, this will give us the last element. We can index into multi-dimensional arrays by separating the indices for, in this case, the two-dimensional indices for the row and the column with a semicolon. So we'll do row 1, semicolon, column 2, and at that particular index of M, the value is 3. if we want to specify an index for the first row of M, we can do row 1 and then do the semicolon, but not put anything for the column. And this indexes the whole row. We can do fancier versions of indices. Here we'll specify row 1 and 1 and columns 3 and 2. And we'll get 4 elements in the result. Next, I'm going to set A to be the alphabet up through Q. And we can index into the alphabet using an array as the indices. So in this case, we can look at just do simple A of P. I'll do A. I wanted to do A. I'll do A of M next. So I don't want the M here. I want A of P. Try that again. And we see that that gives us the letters at whatever the positions were specified by P. Now, if we do this in 2 dimensions with A of M, then we see that since M was a 2 by 3 matrix, the result here will be a 2 by 3 matrix with M being the indices indexing into A. We can use our kind of fancy matrix specification for M with column 1, 1 and rows, or M rows 1, 1 and columns 3, 2 that we did earlier with 1, 1, semicolon 3, 2, close bracket, close, and we see we get EC over EC. We can re-specify either individual elements of our matrices, or in this case, we'll be re-specifying the whole first row of M. So we write the index for the first row, M index 1 semicolon, and then we'll say gets, and then the new values that we want in row 1, 15, 3, and 12, and we'll look at M again, and there's the new first row with the pre-existing second row. Next, we'll define an element Q. It'll be a permutation vector, so it is the numbers 1 through 6, but in a specific order that we want, 3, 1, 5, 2, 4, 6. And then we will use this particular ordering to get a permutation of our vector P. So we'll say P of index, try that again, P of index Q. There we go. And so this gives us a different ordering of Q. We can even have Q index itself and get a different ordering displayed for Q. As I mentioned earlier, the default index origin in APL is 1. So if again, we look at the third element of our vector P, the third element was 5. We can change the origin by using a system command, right paren origin, and set that to 0. It tells us that it was 1. And then we'll look at P of index 3. It's no longer representing the third element, but it's representing the fourth element. The index is, well, if we'll go back and look at in the first 3 elements, 0, 1, and 2, and then we get 2, 3, and 5. The index origin also affects iota, so we can look at iota 5 being 0, 1, 2, 3, 4. And if we want to look at the first 3 elements, again of P, but this time using iota, for iota 3 being 0, 1, and 2, we see that that works as just as well there. I'll change the origin back to 1. And if we look at iota 5 again, we see that it has indeed been changed. Okay, moving on to looking at some functions on arrays. I'm going to start by specifying 3 new vectors, v, m, and n. V is going to be a vector of 3 random integers chosen from 1 to 9. And the way that we write that code is we use the question mark operation, which is called roll, of 3. So we want 3. In this case, a linear array of 3 elements taken from the numbers of 1 up through 9. So the 9 here will specify the range of integers to be taken from. And we'll want m and n to be 2-dimensional random matrices with 9 elements. So we'll do m gets question mark 3, 3, row 9, and n the same, question mark 3, 3, row 9. We'll look at v, 2, 7, and 5. We'll look at m, and we'll look at n. Okay, so we see that we did get random numbers of between 1 and 9 for each of the elements of those vectors. We can add m and n by doing m plus n. This will add the 2 vectors element-wise. We can see the maximum of m and n, again element-wise, by doing m max n. We can do a comparison of m and n. We'll say, show us where m is less than or equal to n. And where you see the 1s showing up in this resulting matrix, that's where this condition is true, and the 0s is where it's not true. We can do the sum reduction. Remember, v is just a linear vector. We can add those elements together with a sum reduction using plus slash v. We can do a product reduction by putting the multiply symbol first. We can use plus reductions and multiply, of course, over 2-dimensional matrices. But we have to think what order, by rows or by columns, will APL do that reduction. So let's take a look at this. We can specify the first dimension by putting a 1 in square brackets and then our 2-dimensional vector here. So if we remind ourselves of what m was, this is adding up the values of m row by row. So we get 5 plus 7 plus 4 is 16, and that's in the first position of the reduction. The second column of m is 2, 7, and 5. So those sum up to 14, and so on. If we look at doing this by the second dimension, we see that this is adding the columns across, so we get 5 plus 2 plus 1 is 8 in the first position, 7 plus 7 is plus 9 is 23, and so on. If we leave out the position and just do the plus reduction of m, the default is by the last coordinate, which in this case would be over rows. We can do the maximum over the last coordinate. Now, in this next segment, we'll be looking at using the slash operator as the reduction for some trigonometry functions. So we'll set x to be 1.5. Now, if we remember how these work, we use the circle command, which is the basis for all of these circle functions. A 1 in front of the circle represents sine, a 2 represents cosine. So the sine of, I put in 1.5, but I meant to put in x there. So I'll do the sine of x, the cosine of x. Okay, so with that reminder, then we'll do plus reduction over sine cosine of x squared. So raised to the power of 2. So this is a way of representing the sine squared plus the cosine squared of x. And the trig identity for that is it's equivalent to 1. Okay. This next expression will represent the sine of the cosine of x. So we'll do circle slash 1, 2, comma x. This next operation is more complicated, and I'm not a trig expert, so I don't know exactly how this is equivalent, but the tutorial tells me that this is equivalent to 1 minus of the cosine of x quantity squared, and then all of that raised to the 1/2 power. So y gets the circle operator slash 0, 2, comma x. And we'll look at the value of y, and we'll compare that using y equals to the sine of x. So 1 circle x, and its equivalent. So whatever that previous more complicated expression was, it is, there's a trig identity there that's related to the sine of x. So now moving on to some more complicated operations with our two-dimensional arrays or matrices. We're going to do an ordinary matrix product, and the way that we write that is m plus dot, which is the period, times n. And so this gives us normal ordinary matrix multiplication. We want to do an inner product using a different operator. We can do m plus dot, and this time we'll use the less than or equal operator. I did equals. Let me just finish this, and then I'll do less than or equal. So m plus dot less than or equal to n. We can do an inner product with a vector as the right argument. So we'll use v instead of the two-dimensional vector in here. M plus dot times v. Remember what v is. 2, 7, and 5. And there's m also. We can do the outer product, which is essentially giving us a times table. In this case, we'll use not period, but we'll use jot first, which is shift J, and then the period times. And then I'm going to use the index generator iota to get the numbers 1 through 5. So the first column you'll recognize is v. The second column is v times 2. The third column is v times 3, and so on. Can get the outer product of v with elements 1 through 9 by doing v jot dot less than or equal to iota 9. Can do an outer product of rank 3 by combining v on the left with not just a one-dimensional vector like we did above with iota 9, but in this case with our two-dimensional vector m. So we'll do v jot dot times m. And so we see the values of v, 2, 7, and 5, have been multiplied by m to give us 3 separate matrices with a essentially a three-dimensional vector with blank lines separating the different planes. So at this point, I'll go ahead and stop this video. In the next video, we will be looking at mixed functions. I hope that you've found this video profitable, and hope to see you back watching future episodes. Thank you.